look at this. This was folded over when they cut this, and there's no hole. Last time we looked at limits where y becomes arbitrarily large as x approaches a number, such as what happens to 1 over x squared when x approaches 0. And we write that as limit as x approaches 0 of 1 over x squared equals infinity, right? And infinity this is the symbol that we use to mean that the graph grows arbitrarily large. So today, we're going to let x grow arbitrarily large and see what happens to f of x. So in other words, so far we've been looking at what happens to y as x approaches a certain number. Now we're going to see what happens to y if x goes out to infinity. So here's a function, x squared minus 1 over x squared plus 1. So what happens to this function as x gets arbitrarily large? Okay, well, here's the table that I made. So you can see as x gets bigger and bigger and bigger, y seems to get closer and closer to the number 1. And if we look at that on Grapher, you can see, sure enough, here's the number 1, and it kind of dips down, and then it gets closer and closer to 1 as we go out to infinity. Okay, so in fact, it looks like we can make f of x arbitrarily close to 1 by taking x sufficiently large. We write that as the limit as x approaches infinity of the function equals 1. So we're using the infinity symbol to mean that x grows arbitrarily large. But here we're saying that as x gets arbitrarily large, then f of x gets closer and closer to some specific value. So generally, we would say that as x approaches infinity of f of x equals L, to mean that f of x gets closer and closer to this number as x gets larger and larger. So remember again that this symbol is not a number. It means that x is getting arbitrarily large. So we frequently say that x is approaching infinity, but that isn't actually true. It's not actually approaching anything. Instead, x is leaving the building.
Ladies and gentlemen, Elvis has left the building.
So there are actually a lot of ways that a graph can approach a number as x approaches infinity. We saw one, but it could even go, if this is the x-axis, this is maybe 1, it could come up and then go down like that. Or it could even, interestingly, it could actually wiggle around it, go above and below it, but then get closer to it as we go out, okay? All of these are ways of approaching a specific value at infinity. So, of course, as we saw in that graph that we just looked at in Grapher, where it went like this, x can approach infinity from either direction, and f of x can approach some number as x gets larger in either direction. So the function that we looked at approaches 1 in both directions, and so we could write also that x approaches negative infinity of that function to indicate that as x gets larger in a negative direction, the function also approaches 1. And again, the same as with positive, there's a lot of ways that a number can approach a value in the negative direction, or it could wiggle too, okay? So last time we talked about vertical asymptotes. So there are also horizontal asymptotes. So the definition of a horizontal asymptote is the line y equals L is called a horizontal asymptote of the curve y equals f of x if either the limit as x approaches positive infinity of f of x equals L or the limit as x approaches negative infinity of f of x equals L. So of course, in the example we just showed, if it goes down and then back up, then y equals 1 is the horizontal asymptote. So it's actually possible for a function to have two horizontal asymptotes. For instance, y equals arctan x. Quickly, of course, a lot of books use tan minus 1, and this is fine. I don't think it really causes any confusion, but sort of technically, there is an ambiguity here because sine squared of x means sine x squared, right? So if this is true, then you would think that this equals tangent x to the minus 1, meaning, 1 over tan x. But it really doesn't cause any confusion. First of all, because there's always a name for this, because 1 over tan equals cotan, right? And then 1 over sine would be cosecant and so on. So it really didn't cause any confusion, but at the same time, we have words for it. There's no confusion here, so I'm going to use arctan just to keep it crystal clear. So the graph of arctan looks like this. As x goes out toward infinity, it approaches pi over 2, and as x approaches negative infinity, it equals minus pi over 2. And of course, this follows from the fact that arctan is the inverse of tangent, and remember last week we demonstrated that tan has vertical asymptotes at pi over 2 and minus pi over 2. So this is just the flip. So we could even have a complicated graph that has several vertical and horizontal asymptotes. So for instance, with this graph, the values become large as x approaches negative 1 from either direction. So we would have the limit as x approaches minus 1. Say this is y equals f of x. Of f of x equals infinity. As x approaches 2, it goes down and up. So if we approach 2 from the left, of f of x equals minus infinity. And then if we approach 2 from the right, it goes up to infinity. So it would be limit as x approaches 2 from the right of f of x equals infinity. Then in addition to that, as x approaches infinity, it looks like it's approaching, there's an asymptote here at 4. And then as x approaches minus infinity, so this graph would have 2 horizontal asymptotes and 2 vertical asymptotes. So we can, of course, define this behavior as x approaches infinity precisely. When we defined the behavior of where there's a vertical asymptote, what we did was we replaced in a regular limit, the definition was that f of x minus L is less than epsilon. When we defined functions that go to infinity at some number, we replaced this with f of x is greater than n, no matter how close we get, right? No matter how big you get n, you can find a interval here that will keep f of x above that line. So now we're going to do the same thing, but instead of replacing epsilon, we're going to replace delta and say that as x is bigger than any arbitrary number, then we're going back to f of x will be closer and closer to some interval this way. So the precise definition of the limit as x approaches infinity is, let f be a function defined on some interval from a to infinity. Then the limit as x approaches infinity of f of x equals L means that for every epsilon greater than 0, there's a corresponding number n such that the difference between L and f of x is less than epsilon whenever x is greater than n. So in other words, what this is saying is that the value of f of x can be made arbitrarily close to L as long as you make n big enough. To look at a graph, what this means is if we have a function that goes like this, and here's L, and we have an epsilon here and an epsilon here, then you can keep f of x inside this interval if you just make n big enough. So that if epsilon is big, then anything, then n even here, if x is greater than n, f of x is always inside that interval. But if you make epsilon a lot smaller, then the interval around L is much narrower. But if you take an n way out here, then x greater than n will still always guarantee from this point out that f of x is close to L, within epsilon of L. Now, the same definition works for negative infinity. You just have to flip all the appropriate terms. Okay, so that's what we mean by the limit at infinity. And there's actually a lot more that we can do with this concept. It's actually very helpful for us to figure out more about how functions behave. First, let's just look at an example. So let's use the precise definition to find 1 over x as x approaches infinity and the limit as x approaches negative infinity of 1 over x. So first notice that as x gets larger, 1 over x gets smaller and smaller. 1 over 100 equals 0.01, 1 over 10,000 equals 0.0001, and so on. So in fact, by making x big enough, we can make 1 over x as small as we want. So that's true of as x approaches infinity, and it's also true as x approaches minus infinity, because even though as x gets larger negative, this function is negative, it's still getting closer and closer to 0 as you go out. So this equals 0 and this equals 0. So the x-axis, y equals 0, is a horizontal asymptote of this function, and it is, of course, the hyperbola. Like that, right? So y equals 0. This is the asymptote. It approaches 0 in that way. It approaches from the bottom, going out this way. Okay, so let's prove that this is true, because it looks like it's true. Let's prove that it's true. So first, always when we're doing these proofs, so we try to guess our rule, and then we'll prove that that rule works. So what we need is, given epsilon greater than 0, we need to find an n such that 1 over x minus 0 is less than epsilon. 1 over x is getting closer and closer to 0 whenever x is greater than n, right? So no matter how big n is, we can always make 1 over x closer. So first, we can assume that n is greater than 0. This is similar to something that we did with regular limits. When you're trying to prove a regular limit, if delta equals 1 works, then anything smaller than that's going to work too. It's the same thing here. If n equals negative 10 works, then anything bigger than that's going to work. So then n equals 0 will work as well. There's no reason to look at anything smaller than n equals 0. So if n is greater than 0, then we can assume that x is greater than 0, right? Because x is greater than n. So we have that 1 over x minus 0 equals the absolute value of 1 over x. But if x is always greater than 0, that's the same as 1 over x. So therefore, plugging this in up here, we have that 1 over x is less than epsilon when x is greater than n. Multiply both sides by x, divide both sides by epsilon, and switch them. So we'll have that x is greater than 1 over epsilon. Okay, so x is greater than 1 over epsilon when x is greater than n. And that's what we needed. So we have that whenever x is greater than n, x is greater than 1 over epsilon. So this suggests that if we set n equal to 1 over epsilon, that should work. Okay. So let's prove that works. So remember, what we're looking for is actually a rule such that whatever epsilon you give us, I can plug your epsilon into my rule and give you an n that will make our statement true. Okay, so given epsilon greater than 0, we choose n equals 1 over epsilon. So now we have to prove that when x is greater than n, 1 over x minus 0 is less than epsilon. So first of all, if n equals 1 over epsilon, we can multiply both sides, divide both sides again, and we get that 1 over n equals epsilon. So now assume that x is greater than n. And also notice that since epsilon is greater than 0, 1 over n is greater than 0, that means n is greater than 0, so x is greater than 0 too, so everything's positive. So now we showed above that 1 minus x over 0 equals 1 over x. We just showed that. So since x is greater than n, then 1 over x is less than 1 over n, and that equals epsilon. And that's what we needed to show, because we know that 1 over x equals the absolute value of 1 over x minus 0, and that is less than epsilon when we start with this assumption. So that's what we needed to show. Good. So therefore, the limit as x approaches infinity of 1 over x equals 0. Okay, good. This is a good place to stop for now. Next week we will look at the limit laws as x approaches infinity, and also prove a new theorem that will be helpful for figuring out the limits of a function as x approaches infinity. Thank you. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.